Welcome to Analog Microelectronic Circuits lecture. This is lecture number 10 of Unit 2. So far, the previous 9 lectures we were spending on BJT to understand its operation, small signal models and various configurations. So in previous class, in yesterday's class, we discussed about common collector amplifier, common collector configuration, and we have derived its voltage gain, then input resistance and output resistance, right? So before discussing about the other configuration, which is common emitter with a degeneration, let us start with a very simple numerical where you can apply the concepts what we learned in the previous class, right? So let me give you one question here. Yes. So the question is this. You have a BJT where a resistance is connected to the emitter, right? Now this is connected to some DC voltage. Now given that the emitter current is 0.18 milliamps, beta value is 49 for the BJT. Now this resistance is 800 ohms. The question is, uh, you are asked to find the resistance seen this side, which is Rin. When I say resistance seen this side, a resistance measured at the base with respect to this point. This point is, you can think of this as a ground point or the reference point. Maybe I'll mark like this. This is R in, and resistance from the other side, which is R out, right? So you are asked to find what is R in and what is R out. You can wait before posting answers. I'll ask you to post and then you can start posting. But anyway, all of you can start working on this numerical and get the answer for R in and R out. All right. So any,
So,
yes.
so terminal voltage, sir, VT,
Yeah, VT you can take. Assume it is room temperature.
26
Yeah,
millivolt.
26 millivolt. Yes.
Okay, sir.
Okay. Now, Krishna Pratik.
Yes, sir.
Yes, Krishna Pratik. So can you help me out in solving this numerical?
So I didn't get the question. R in is between base and ground,
Yes. Ground. Yes.
and R out is
Where is R out marked?
mm, one end of emitter and ground.
Yes, between emitter and ground. Yes.
Oh.
So how will you start this?
Mm, You can find the voltage at that point,
Which point?
uh, the emitter point.
How will you find the voltage?
Okay, no, can't. So I'm not sure. I don't know.
All right, Krishna Pratik. Definitely, but we
Then
will, yeah, we will interact.
I had one doubt.
Yes, yes, yes.
Like, when are we supposed to include the emitter resistance, the small RE?
Small RE,
Like in the mm, yeah, in the gain for common emitter, that time we haven't taken that resistance.
common emitter. This is the common emitter circuit, right?
Mm. Here that resistance RE is not taken.
But what is RE, or what is the relation of RE and R pi?
R pi is RE into 1 plus beta.
Yes, so RE is taken into account, right?
So that you don't have to include a separate resistance from emitter terminal to ground.
No, I'm not getting. What is what is the terminal? What is the resistance between emitter and ground? What is that?
So what is RE exactly? Small RE.
Okay, what is your understanding on RE?
I thought that's the resistance at emitter terminal.
Okay, in the sense you meant that that is a resistance added externally.
No, not that.
Probably, I think Krishna Pratik, you did not follow the initial classes.
So only the RE part I'm not understanding.
That is what we have done. That we have included it. Probably you would have missed that class, or yeah. So here actually we have brought in all the small signal parameters, RE and RPi and other things. Yeah. So there is no resistance between emitter and ground, right? So what we are keeping here is a small signal model of a BJT. So if you remember, what is a signal, the equivalent, the AC equivalent or a small signal equivalent of a diode? What is equivalent?
Resistor.
It is a resistance. What is the value of that resistance?
It will be 26 millivolt by the
VT by
current that flows through it.
the diode current, right? So this is the what we have drawn here as the small signal equivalent as resistance is the resistance of this PN junction.
Mm.
That is for a diode. Now look at the case of a BJT. You have a BJT, so there is a PN junction here which is forward biased. Now this is equivalent when your diode is actually forward biased, right? Now,
Mm.
when I use a transistor, especially in active region, this junction is forward bias. This PN junction is forward bias. Now, between
Mm.
emitter and base, you have a resistance.
Mm.
That
Yes, sir.
resistance is called as RE, what we call as RE, which is actually VT by IE.
Oh.
Right.
Mm.
So the resistance is between base and emitter. Now, why are we not? So when I look from emitter, the resistance is RE only. That is what I don't know. If you have followed the rest of the classes, you will definitely say the resistance looking from emitter is RE. What is RE? RE is equal to 1 by GM.
Mm. Yes, sir.
But now the same resistance, if I see from base, that will be beta plus 1 times RE. That is your R pi.
Oh.
Why is it so? Because the relation between the emitter current and base current is beta plus 1. Your emitter current is beta plus 1 times your base current. That is how the
Mm.
resistance looks different way. When I see from emitter, it is Re, but when I see from base, the resistance is Re into beta plus 1.
Mm. So that RE is already included in the R pi when you're looking
Ye-
from base.
Yeah, yes, of course, no, because
Okay.
what is R pi? R pi is beta plus 1 into Re.
Mm.
All right.
Okay.
So
Got
there is
it, sir.
no, yeah. So there is no resistance connected from emitter to ground. So if I do that, that is an external resistance adding. But now this
Mm.
RE is the internal model. RE is actually we call it as RE model. So why I haven't brought the RE model into picture is just to have a similarity with whatever analysis we have done for MOSFET.
Mm.
Right. I should have. I can actually do in a different way. What I thought is after doing all the analysis, I'll bring you the other way where I write in terms of RE. So just to avoid confusion, I did not bring it in the beginning.
Okay, sir.
All right. Okay. Now tell me, Krishna Pratik, how will we start with this? How will I find Rn?
So I'm not sure. I need some time.
All right. So you should definitely follow the classes, Krishna Pratik.
Yes,
Right.
sir.
Yeah. I think you have missed in the sense you would have kept pending the lectures, the previous lectures.
Yes,
That
sir.
should
In
not be the
starting, I
case.
didn't.
Yeah. So if you do that, the problem is we will you will not you'll not be able to follow the rest of the lectures, and at the end it will be like a lot of lectures pending, and we will end up by saying that the subject is tough.
Yes, sir.
Right. Yeah. So please don't repeat this again. All right, Krishna Pratik. Yeah. So are there any answers for this question? If some of you got answers, you can post here the value for R in and value for R out. Pallavi, yes, your answer is 47 and 122.3. Both are slightly different. Okay. Muthu Subramanian, yeah, you also got the answer, 47.2. Yeah, answers are close, but not the exact answer. So I don't know whether you have taken VT as 26 millivolt or not.
Sir, I took RE as alpha by GM
Okay,
instead of 1 by GM.
okay, okay. But RE is anyway VT by IE, right?
Yes, sir. Maybe some calculations.
Yeah, yes. Okay, so yeah, I'll just tell you how to approach this. If you have followed the previous lecture, this is as same as finding the input impedance and output impedance of a common collector amplifier. You can see that your collector terminal is common, and you can follow the same way, the exact same way what we have done for your common collector. So I will replace transistor with its equivalent. This is R pi. This is GM pi. Right, this is the equivalent of transistor. There is no information about V naught, right? Sorry, R naught. So I will not include that. Now I have to add an external resistance which is 800 ohms here. Now the first thing is you should find the input impedance from here. So I will mark this as V test, I test. I will not write all the steps here. So when you do this, your result will be something like this. Your Rin, you will, yeah, can you tell me what is the equation for Rin? I can go back and look at the input impedance expression. It is the same thing here. The equation is beta plus 1 times small re into capital RE. So it is beta plus 1 times small re plus capital RE. Now what is small re? Small re can be written as Vt divided by IE, which is small re. Vt is 26 millivolt divided by IE is 0.18 milliamps. So that will give you small re as 200 ohms, right? So this is small re, capital Re is 800. So it is 1K into 50. That is your Rin. Your Rin is equal to 49 plus 1 into 200 plus 800. It is 1K into 50, which is equal to 50K. I don't know how you are getting Rn as 46. Can one of you unmute and tell me how this Rn calculation is, because Re is anyway 200. So what?
Sir,
Yes.
sir, RE is coming as 144.44.
How is
Yes,
it?
sir. So 26 by 0.18, we are getting 144.44
Oh, is it?
ohms.
Oh, then I made a mistake. 26 by 0.18 is 144. Oh,
Yes,
sorry.
sir.
Oh, very sorry. Really sorry. Then you are right. I think. I don't know. This is equal to 144. Right. Very sorry for that mistake. So this is 144. Then it is correct. I think you all did correct. So the answer is around 40. this is coming 944 into 50, right? So somewhere around 47.2k. But still there is a difference. You know, some are getting 46.88 that I didn't get. Yeah, so this is Rn. Now, tell me if there is any mistake in my calculations. Now, what is R out? What is R out in this case? Okay, let me check with one of you. Renuka, are you there? Renuka? Renuka? Tanush? Okay, Nishant?
Yes, sir.
Yes, Nishant. Can you tell me how to evaluate R out?
Same, sir. We test and I test in the emitter.
Yes. So this 800 is coming anyway in parallel to that, right? So I can I keep 800 separate and find the rest and make it in parallel? And Nishant, I'm waiting for you to respond.
Yes, sir.
All right. Okay. Okay, Nishant. Yeah. So this is 800. And what is the parallel resistance here? So what is the parallel resistance, Nishant? Oh, Nishant is also not there. Okay. So R out is 800 in parallel to the resistance seen from here, which is equal to what is the resistance seen from here? As I told just now, it is Re. So Re is 144. So what is the parallel combination result? I think it is close to 122 ohms. Right. Yeah. So that is about this numerical. So these kind of numericals you may get to evaluate input and output impedance in between. All right. So let us quickly look at this configuration, which is common emitter amplifier with, sorry, it is not source degen, it is with emitter degeneration. All right. So now for this, I will give you the circuit diagram. This is RC. This is your BJT. Then there is an RE resistance here. Now this is V in and this is V out. Right. So this is your common emitter stage with degeneration. Now, as we have understood MOSFET amplifier based on source degeneration, we know that the circuit basically improve linearity. I hope you remember about this. I mentioned in common source amplifier, this generally the addition of this resistance will improve linearity. Anyway, let us try to find the voltage gain of this circuit by keeping the small signal model into consideration. So can you guys work it out and tell me what is the voltage gain of the circuit? Voltage gain of the circuit. Okay, so to evaluate that, you have to replace this with the transistors model. So R pi, this is GM pi. So this is This is transistors model. Anyway, R0 I'm not including. Now I'm adding components which are there in the circuit. So I need to add an RE here. This is RE. Now output is taken from the collector. So I have to add the resistance RC like this. Now this is V in point, this is base, this is emitter, and this is collector, right? So the voltage across R pi is actually V pi, that also we know. Now what we have to do is we have to write equations to evaluate what is V out by V in, right? So you can try out in different forms, different ways. You can do that. I'll take this route. So I know that the current, there is a current actually, the voltage here is V out. So V out by RC, there will be a current, right? Now that current is equal to GM pi because this is only the path, the only path. Now if I have current in this form, I can write it as 0 minus V out by RC, that is this current, that is equal to GM pi, right? That means, so what I'm trying to do here is I'm trying to get an expression for V pi in terms of V out or V in so that I can substitute and eliminate that. So I can write V pi as minus V out by GM into RC, right? This is our V pi. Now, when we look at the circuit diagram, we also understand that there are two currents flowing through RE. One is a current coming from this side GM V pi. Another one is actually this current that can be written as V pi by R pi also, right? Now, if I write the total drop across this emitter, if I write it as VE, let me write the emitter voltage VE as the total current is, one is V pi by R pi, that is one current, and the other current is GM into V pi, both multiplied by RE. This is actually the voltage at emitter, right? Now we have written an expression for V out in terms of V pi. Now if I look at the input side, I can write that my input voltage V in is actually the sum of the drop across this R pi and the drop across this RE. So I can write as V in is actually V pi plus VE, or if I write this, I can write it as V pi plus V pi by R pi plus GM V pi into RE. This is V in, right? Or this can be, you can actually do this in different ways. You can take out V pi also from this. So I'll take V pi out from this. It is 1 plus 1 by R pi plus GM into RE. So this is V in. Now V out can be written as GM minus GM RC into V pi. Now just take the ratio of these two. So V out by V in can be written as V out by V in is equal to minus GM RC into V pi divided by the other term is V pi into 1 plus 1 by R pi plus GM into RE, right? This makes it very simple. It is V pi I can cancel. I can write V out by V in as minus GMRC divided by 1 plus 1 by R pi plus GM into RE. In fact, we can actually simplify this denominator term. We can, if you want, we can write in terms of beta. But what we will do is we can actually okay, just to simplify this, I can say that okay, now GM, yeah, this GM quantity is actually larger than 1 by R pi, because what is R pi? R pi is beta plus 1 into RE, right? So if you look at these two terms, we can say that since r pi is large, 1 by r pi will be very small, and that can be actually neglected. So if I do that, this can be further approximated as minus gm rc divided by 1 plus gm into re. Right. So why I have done this approximation is just to have a comparison with what we have done for common source with degeneration. If you remember that the formula was minus gm rd divided by 1 plus gm rs. Both are same.
Excuse me, sir.
Yes.
Sir, alpha value is, will be moderately low, no, sir?
R pi is beta plus 1 into re, right?
Oh, okay, sir. Okay, correct.
Yeah. Okay, I can rewrite in this form. So what I have here is 1 by re into beta plus 1 plus 1 by re. Right. So the you can see gm is 1 by re, right? Now I have these two terms. So re is small, but this is actually a large term. So out of this, this can be this is just an approximation. So this can be a significant term. So I am just neglecting this 1 by r pi and writing it in terms of this. So it will be minus gm rc by 1 plus gm re. The expression remains almost same. But you can see that for a common emitter amplifier. So for your common emitter amplifier, your gain was minus gm rc. But now by including this degeneration resistance, by including this with emitter resistance, your gain is actually falling by 1 plus gm re, right? Because now the gain is minus gm rc divided by 1 plus gm re. So gain is reducing, but still why are we going for the circuit is actually because the circuit improves linearity. I can give little more clarity on that about linearity. Okay, so that's about this common emitter amplifier degeneration. Now you can repeat the same with including R naught. So you can see that when you try to include R naught has to come like this. R naught has to come in this form here. Now, to do the analysis, what you can do is you can actually convert this current source in parallel with the resistance into a voltage source in series with the resistance, and you can follow the same procedure of the common source amplifier in order to arrive at the expression. So that you may do as homework. Right. Now for this output resistance we also already calculated. If you look back for the circuit where we have done the output resistance calculation, I think we have done it's somewhere here. Yeah. So this is the output resistance value R naught into 1 plus gm into r pi parallel re, which is output resistance. This we have done already, right? This we have done including R naught. So let me just take out that formulas and write it here. The R out value is that. Now what about R in? So how will be the R in value? Looking at the circuit. So what will be R in? R in is a resistance seen from here, right? Any idea? You can try this, and we have done actually whatever we have done just now is same as Rn. So you can try this and check whether you are getting this formula beta plus 1 into Re plus Re. That will be your Rn formula, and your R out formula will remain the same as what we did before, where you have R out value. Let me copy the same value from here there. This is approximate, right? Yeah, approximately this. This is R out. This R out is including small R naught. So that I'm leaving for you guys to work it out and get the answer for this, right? So this is your common emitter amplifier with the degeneration resistance. So if you look at all these configurations, whether it is common collector or common emitter, everything remains same. The things will become easy once you are familiar with the small signal model, right? Today I am winding up here, but we'll definitely have some interaction. I just wanted to know what clarity you have on this small signal model. So let's have discussion now.